Let's start with Bitly. It's the easiest one to begin with of all the systems that we'll be discussing in this video. So at a high level, what is Bitly? Bitly is a URL shortening service that converts long URLs into shorter, manageable links. It also provides analytics for the shortened URLs. So ideally, as we keep discussing, I should list down the requirements, break down into functional and non-functional. But given the breadth of the content that I want to cover in this video, I have listed down way before. That's fine. The main intent of this is to just to understand if someone throws a questions of these requirements and puts us in a situation to reason up to build a system which supports these requirements. Yep, so it's very clear here now. The requirements, the functional is user should be able to create short URLs from original URLs with an optional options like they can provide the custom aliases and the expiration date for the short URL. And the other functional requirement is user can access original URL by browsing through the short URL. And non-functional is alright, the shortened URLs whatever we will be providing, they should be unique. There should not be any collision between multiple original URLs, and the redirection of the shortened URL to original URL should be less than 100 milliseconds, and we should give high priority for availability. That is, redirection service should always be up and running, giving higher priority for availability than consistency of the data. And the last requirement that we should satisfy is we should support 1 billion URLs and 100 million daily active users. So these are the requirements that will be thrown at us and has to build a system which supports this and reason up for the choices that we will be making and to drive the conversation through various phases of the system. So once we have the requirements clear, we should identify the core entities that are involved in this system. So looking at the requirements now, we can straight away say that the core entities that we'll be dealing with is original URL, short URL, and the user entity. So that's the second phase. We should clearly list down the core entities. So the second step is going to be listing down core entities. It's not needed to list down right away all specific columns, its types, and the sizes of each column. So if you can see here, original URL, that is the actual original long URL that the user wants to shorten. And the second one is the shortened URL that the user receives and can share or browse. The third entity is user, which really represents the user who created the shortened URL. So once core entities is clear, that is going to lay the foundation for the next phase, which is the API phase that we'll be discussing. So this sets up a contract between the client and server. Actually, this is the first point of reference for high-level design. It is very clear each endpoint is going to serve one of the functional requirements that we have. So to shorten a URL, we will need a post endpoint. So, and I'm just naming it as something like short_URL. So this endpoint takes in a long URL along with the optional options like custom alias and expiration date. Taking this as a payload, it will return the short URL. So this is the endpoint which helps us to achieve the first functional requirement. The second one is the get endpoint, the redirection one. So we'll need a get endpoint which takes in a short code and redirects the user to original long URL. So simple one takes in short code, let's say example abc123 or whatever, and it redirects to the original URL with HTTP 302 status code. We'll talk more about status code when we are going into the high level design. So next phase is high level design. So this is the phase, the fourth phase, where we'll try to go through one by one of our functional requirements and try to design a single system to satisfy them. Once we have this system in place, then we will try to layer on depth via our deep dives. So let's talk about the first user flow. So first user flow is basically users should be able to submit a long URL and receive a shortened version. So here the core components that I have listed down here is the client. The client is basically, that's where users interact with our system through either a web or mobile application. And the other component here is the server. This is our primary server which receives a request from the client and handles all business logic like shortening, URL creation and validation and other stuff. And then the third component I have listed down is the database, which stores the mapping of shortcodes to long URLs as well as user generated aliases and expiration dates. So to reiterate on the flow, ideally when a user submits a long URL, the client sends a post request to short_URL with a long URL, custom alias and expiration date. The primary server receives the request, validates the long URL just to ensure the URL is valid and also make sure that this URL is not existing in our system, which we can confirm by querying the database. So once we make sure that URL is valid and it is not existing already in our system, we can just proceed to generate a short URL code for that. For now, let's not talk about how we are going to shorten the code. Let's just keep it in a black box, kind of like abstraction layer. We'll talk more about that in our deep dive sessions. So, and consider also if user has specified a custom alias, we can use that as a shortcode and then process that and try to insert into our database, storing the shortcode, and finally we can return that shortened URL to the client. So that's how ideally the flow for our first functional requirement is going to look like in our high level design, talking to each component. So you can see we generate a short URL, saving to DB, and we do validations, and then now listed down the fields that we'll have in our database: short URL code, original URL, created time, expiration time, created by, and other user related entries. So at a high level, this is more than enough to just to highlight what fields we'll be storing in a database. Let's talk about the second phase now. Second functional requirement: user should be able to access the original URL by passing the shortened URL. So now our short URL which we return in our first flow, it is live and user can access that original URL by using the shortened URL. So this shortened URL exists at a domain which we own. Okay, for example, we can say it is like os.ly or anything, something like that. So short URL would look like os.ly/abc123 or whatever it is, and all requests to that short URL will go through our primary server which we have here in the center of the screen. So the flow is going to look like this. The user is going to access shortened URL. The following process occurs. The user browser, which is a client, sends a GET request using our shortcode endpoint to our server. Let's say, like I said, /abc123. Our primary server is going to receive a request and it tries to looks up the shortcode in our DB. If shortcode is found and isn't expired, then we try to return with the 302 redirect status code. So here to talk about what is this 302 redirect code, and why not 301 redirect code that should be returned. So to at a high level, 302 redirect is basically temporary redirect. This always ensures whenever user is trying to browse through that short URL, it goes through our server. And if this happens, we'll have more control on making that URL expired, or maybe keep track of some analytics like number of clicks, geographic statistics and all, though it's not in part of our requirements. But to have a more control on such operations that we can perform, it is recommended to return with 302 redirect. And also this helps browser to not cache a response, so that is very important. 301 permanent redirect, this lets the browser cache a response for the first time, and further visits will bypass our server, which definitely is not going to meet the requirements that I just specified, and it's not going to be in our control if you wanted to invalidate, or if that short URL is changed, because it will be cached and it will be stale data that the user will be still trying to redirect to, or it can receive an error. So that's why we always try to redirect with the 302 sections. So this is the second user flow of trying to access original URL by using the shortened URL. I think now it should be a clear how the flow is going to happen when user provides short code, and now we are going to deal with our system that we have designed. So let's jump to the deep dives. So deep dive is basically whatever we have each point in a non-functional section. We'll try to take one point at a time and discuss how we are going to achieve that. So the first thing, like I said here, each point in non-functional section, we'll try to discuss one thing at a time. So we should ensure the shortened URLs are unique, making sure there's no collision between whatever the original URLs that we are going to receive. So how are we going to achieve these constraints? That is unique shortcodes, and try to keep it as short as possible, and the generation should be efficient. Let's try to brainstorm the approaches. So let's discuss on how we can achieve making sure that URLs are going to be unique. So the brute force approach that we can straight away think through is whatever the long URL that will be receiving. So here let's maybe focus on the first n characters prefix of a long URL. So here shortcode will be just first n characters of a long URL. Let's say the long URL that we are receiving is www.google.com/test, and the I'm considering it as a 6. So www.go is going to be our shortcode. So this is not going to work, and it's going to clearly violate our unique constraint. Why? Because let's say we are receiving one more original URL, www.google.com/hi. The first 10 characters here, it's going to be www.go. So it's a collision between this URL and this URL. So our system will really not have a clue to which original URL it should redirect the user to. So it really violates the unique constraint, and this is not the option. The other option that we can think of is random number generator or hash function. So it's basically we'll try to use a standard math.random or crypto functions for increasing unpredictability to generate some random number, or use hash functions which always returns deterministic and fixed size characters. Once we get the random number from either of the random number generator or hash function, we try to encode using base 62. So base 62 is basically, it's a alphanumeric characters like A to Z of lowercase, A to Z of uppercase, and 0 to 9. Once we encode using that, we try to take first 10 characters and consider that as our shortened code. and usually n is determined based on characters needed to minimize collisions. I'll talk more about it on our deep dive. Here let's take in as example, the input URL is going to be something like this: google.com test, are you there, something like that, and random number, it's going to generate some random number, and I'm going to pass this random number to this base62 encode function, which gives us some code, and I just try to take first 8 characters. And this is the approach we can consider. But there is a challenge in this approach as well. So let's talk about the challenges. So here, as URLs increase, the chance of collisions dramatically increase as well. So this is a standard birthday problem. It's a kind of a paradox. So to at least explain to in a simple way, I can say something. Let's say let's just picture there are 365 lockers in our gym or school, or in any sports academy that you're visiting, whatever. So every person will try to put his books or bag in a random locker. Now after only 23 persons, the chance that 2 people putting books or bags in a same locker is already about 50%, even though most lockers are still empty. That surprise is called the birthday problem. So the same math applies to our the 8 character base62 code as well. So that A to Z caps and smalls and 0 to 9, they will start colliding after roughly, let's say 17 million URLs. So after that, we should check for duplicates or use longer codes. So to avoid that collision, we need high entropy. High entropy, again, it's nothing but which we need more longer short codes. It is against our constraints. We should try to keep our code as short as possible. That's the ultimate solution that we're trying to provide. So as we keep increasing the short codes and the chance of collisions increase, detecting and resolving collisions involves too many database lookups, adding more latency, ultimately leading to trade-off between uniqueness, length, and efficiency. So we should try to fight with any one of these trade-off and compromise on the things. So even if we don't want to take any chances for the collision that is going to happen, this is not the approach that we should take. So the ultimate solution for us to achieve the codes that we are going to generate are unique is to proceed with the unique counter with a base62 encoding. So it's basically we try to maintain incremental counter for each new URL that we are going to receive into our system, and we encode that counter using base62 and store that in our DB. So to achieve this unique incremental counter and also maintain atomicity, the best choice is going to be Redis. So this is going to help us maintain unique counter and make sure that URLs are short codes are unique. So this again saves us for not checking for additional checks if the short code is already present in our DB. And also one more thing, the question that can come up is, should we really worry about the length of the short code as the counter keep increasing? Let's say the counter is at 1 billion value. I don't think we need to worry, because 1 billion counter value, when we try to encode, it hardly gives us 6 characters, which is still smaller or shorter code, and it supports the requirement that we have 1 billion URLs. So let's say we wanted to support 3.5 trillion unique URLs, the short code is going to be of 7 characters. So this is most optimal and the approach to achieve our first non-functional requirements. And it satisfies, but it's not a concern. It's a more of a challenge in a distributed environment, how we are going to make sure that synchronization is present in Redis counter. We'll talk about that. So after we introduce this third approach, the system is going to look like this. The Redis counter is part of our primary server, which keeps track of the unique counter as new URL keeps coming. So this is the new addition to our system design. Yep, that is the first non-functional requirements. That now next is, how do we ensure redirects are super duper fast? By now it should be clear for you, the system that we are designing, it's read heavy, maybe in the ratio of 10:1 or 100:1. Hardly people try to create a new URLs, shorten new URLs. People will be trying to access that new URLs, trying to read that. Okay, so that is why the system that we are designing is more of a read heavy system. So ideally, if we user tries to look up for a shortcode, we try to match for every shortcode in our 1 billion records in a table. That is, we just do full table scans, which really adds a lot of latency and violates our constraints, and also it becomes bottleneck as we scale to our system. So that's not going to achieve the performance or the requirements that we have listed above. So how can we achieve that? How can we make redirects are fast and achieve the latency that we have listed down in our requirements? Let's talk about that approaches. The first thing we can straight away think of is adding an index on the column that we are frequently trying to query. The frequent column that we are trying to query is the shortcode. So we'll try to add an index on that thing, usually a B tree in our SQL database, PostgreSQL or MySQL. So let's talk about how that is going to work. Let's say I have inserted the values into a DB with the short URL code and the original URL, and ignore the other columns for now, ABC1 to 3 and the URLs. And this index is going to maintain in a sortable list. So this because we added index on this short URL code, it's going to sort, and then median becomes a parent, and then all the values less than the parent will be as part of the left child of the parent. All values greater than this parent will be part of the right child, and so on. It will be recursive. So this is how ideally, just for visual purpose, the B tree is going to look like, and each node is going to maintain a pointer to hold record of the info in a DB table. So now let's say user tries to query select star from table where shortcode URL is equals to like something DEF and all. So it is going to find that node in this tree in a big O of login times, and once we find that, it's directly going to access that record in a table and fetch that. It's avoiding full table scan and giving us the result way faster than it used to be. Or that's one approach. In Postgres, there is an hash indexing concept. So basically it's nothing but having an n buckets and trying to place shortcode into respective bucket based on the hash value calculated. So let's say I have bucket 0 and I put this hash value of this shortcode is 0, so I put that into this bucket 0. Same applies bucket 1 and so on. And if there are multiple things, will be kind of a linked list that will be here stored, and then this will be pointed to respective row in the table. And this is how the lookup for a specific shortcode will be way faster. But the challenge here is, if we try to follow this, is here solely relying on disk based access, it possesses challenges. And let's reason up why this is going to pose a challenge for the requirements that we have listed above. So typically solid state drive SSDs can handle 100,000 input output operations per second. So for our daily active users, which is 100 million daily active users, let's assume there are 5 redirects per day. They're 5 redirects per day, And so calculating that 100 million daily active users multiplied by 5, it is going to be 500 million redirects per day. So per second, so 86,400 seconds, maybe 10 power 5, so approximately 5k redirects per second. So this is like ideal traffic we assumed, but this is not always going to be the case. So peak time, let's say, always consider like 100 times or 10 times of actual traffic. So actual traffic is 5k plus. So if it's 100 times, it's going to be 500k plus redirects per second. So it's very clear, these many redirects per second, the SSDs cannot handle the traffic at which it is throwing at our service. So database really struggles to handle, and this causes us the timeouts and the latency issues, and as well downtime on operations like URL shortening. So it's a good, but not going to support for the requirements that we have listed down above. So then what can be the next approach? So the next approach that we can think of is adding an in-memory cache, Redis. So this basically what we do, whatever or frequently accessed short URL code, we try to maintain a mapping for that short code to long URL in a Redis. And this, it's going to improve our latency, because let's talk about the time it takes to access a memory, time it takes to access SSDs, and time it takes to access hard disk drive. So here MET is memory access time. So it's 1,000th of a millisecond, which is way faster to access a records in a memory based store. And SSD level access time, it's 0.1 milliseconds, and hard drive access time, it is 10 milliseconds. And operations per second that memory can handle, it's millions per second. SSD, it's roughly 100,000 input output operations per second, and hard drive can handle 100 to 200 operations per second. So this clearly, the numbers that we have laid out, it's going to handle the latency that we are going to be needing, which is less than 100 milliseconds for redirections. So if we introduce this in-memory cache, and how it is going to look like in our high-level design, the component is basically here the Redis cache that at the top, we will have key to original URL mapping, key, let's say df456, and the original URL will be stored it in this way. So how the flow is going to look like? We first check cache whenever the client is sending a request to our primary server. If it is present, we straight away return to the client. If not, we check DB, then return to the client, and then store it to our cache. So the next time the user tries to query, we straight away return from this Redis. So increasing the response time dramatically. So this is how the updated system design is going to look like. That is the second approach. The last approach that we can really think of when we have the leverage of trading cost and complexity for performance. So the CDNs, we can leverage CDNs and edge computing. Whatever the short URL domain that we have, it can be served through CDN with the points of presence geographically distributed around the world. So whenever users trying to access whichever the CDN is near, that will try to serve from that CDN edge location. And even by deploying the redirect logic to edge using Cloudflare workers or AWS Lambda at the edge, redirection can happen without even touching our origin server. But the downside of this is the problem. Yeah, even I forgot to flag some challenges here. It's the method that we are in favor of for the requirements that we have listed above. The thing that we need to carefully be cautious about is cache invalidation. Basically, whenever deletion or updates happen in our DB, we should make sure that they're updated in our cache. That's one thing. And cache needs warm-up time. So initially if you request, there'll be nothing in the Redis cache, so they have to go through DB, and that's one thing we need to worry about, and that's not of a bigger concern. And then cache eviction policy and size. So whenever cache becomes full, we should have some eviction policy like least recently used and all, keep making sure that eviction policy is properly implemented, and so on. So yeah, the downside of this now CDNs and edge computing is this. Same here, cache invalidation, and the biggest concern is consistency issues across multiple CDN and edge locations that we'll be having. And also setting up edge computing is really configuration and cost overhead, and also debugging and monitoring is way harder in CDNs and edge locations than in our servers. So these are like very important points to consider if we decide to go to this approach. And here we really need to trade cost and complexity for performance, but this is very leastly preferred approach, and it's hard to implement as well, given the complexity for configuration and the cost that is involved. So the approach that we'll be going with is adding in memory cache Redis, which really meets our requirements. So this is the thing. Fine. Now the other point in our non-functional is how can we scale to 1 billion URLs and 100 million daily active users. Let's talk about roughly the database size now. The fields that we have currently is short URL code. Let's assume this is 8 bytes, and original URL, which is like 100 bytes. Created time, let's say 8 bytes. Custom alias 100 bytes. Expiration date 8 bytes. So roughly summing up, it is close to some 200 plus bytes per row. And also consider we'll store some user metadata, and cumulative it's around 500 bytes. And we should support 1 billion URLs. So 1 billion rows multiplied by 500 bytes is summing up to 500 GB. So in reality, this single database easily handles this. Even if we hit this limit over this size of the data, we can shard data across multiple servers, which is very rare to happen. Now we know this system is read heavy, which we are trying to handle using cache Redis cache, and trying to meet the latency that we have. And for writes, let's say we have like 100k new URLs created every day. That is roughly around 1 writes per second. So Postgres easily handles, based on the input output of operations per second number that we saw, it can easily handle, though it is in hard drive disk or SSD disk, it can easily handle 1 writes per second. But the problem here that really comes is single point of failure. If we are maintaining in a single database, the question is, what if the primary database that we are maintaining goes down? So that is the question that we should proactively think through and discuss on that as well. So there are two options. One is database replication. So it's just maintain replica of primary database, and whenever this database goes down, this replica will replace the primary database, and the services will still keep running and it will be functional. The other option is database backup. It's basically we periodically take snapshots of the data in the primary database and store elsewhere, and whenever this goes down, and this will replace the primary database. So these are the two options we can think of to avoid single point of failure. But again, just caution, adding this or maintaining this adds complexity to our design. And the other question is, what if our primary server, which we are handling all our URL creations and redirections in a single server thing. So given the traffic that we are estimating it to receive, it will be really hard to handle, and it will be really hard to scale if we are trying to handle writes and reads in a single server. So the best way is split this primary server into read server and write server. So read server basically handles our get endpoint, which is the redirects, and write server handles our post endpoint, which handles the creation of the new URLs. And this way it really makes us easy to horizontally scale individual servers. So here mostly we need to scale more of a read servers than write servers because it is a read heavy system. So this way we try to delegate the respective functionality to different server, and load will be equally distributed. And now the issue when we try to split this primary server into read and write server is we should try to maintain a centralized Redis instance for write service. So let's say we are trying to horizontally scale write servers. Let's say there are two write servers, and to maintain a unique counter for all of the requests that will be parallelly flowing in through each of the server, we need to have some global counter. So that is the Redis, which ensures the atomicity and the number is unique for all the URLs that will be coming in streams for each of the write server worker. So whatever I discussed now, after implementing this global counter, the final design is how it's going to look like. So the client, and here I add in an API gateway. So the main functionality of this is going to be route the user's request to correct microservice. If it's a get endpoint, redirect that request to this read service, and if it's a post endpoint, route that request to write service. And this write service now should communicate to our global counter, which is the Redis thing, which maintains the counter of the unique number of URLs that we will be getting into our system, and then they will be connected to database. And this is all part of the previous design that we had. Additional thing that is added here is the API gateway to route to correct microservice, which we split our primary server into write server and read server, and then the global counter for maintaining the count for unique URLs. And the other point to really highlight here is, as we keep scaling write service, and if we have to make a network call to Redis for every new URL that is streaming into write service, it's going to have more network calls. The better way to avoid the network calls is to follow the approach called counter batching, which drastically reduces network calls. So this is more of a, like, let's say there are two write service instances, and the Redis counter count starts at like 1000, and worker service 1 requests first batch. Let's say the counter value is at 1000, and this will increase that counter directly by 1000. So the counter will become 2000, and the value of the initial thing, the 1000, will be sent to worker service 1, and worker service 2, which is parallelly requesting the batch of 1000 from this global counter, the number will be increased from 2000 to 3000, and the initial value will be passed on to worker service 2, 2000, and they will have a local batch of 1000 counters in each of a server, so they can process 1000 URLs at a time in a one network call. And whenever the batch is exhausted locally, they can make a network call to Redis later and get the latest count that is present in Redis. This way the network calls for Redis and the efficiency of the worker services will be dramatically increased and makes our system way performant. And this is how one of the technique to reduce network calls. So finally, to sum up, this is the system that we can propose to meet the requirements that we have initially listed out. I think at least it gave a brief idea of how we can think through and flow through the phases and of designing each component at a time and reasoning up for the choices that we make of all the approaches that we discussed. So let's discuss the another system design, which is a Dropbox or a Google Drive, and we'll talk more about how we can satisfy the requirements for that system as well.